Welcome back. So, today we will discuss on alpha migratory insertion little bit and then mainly get into the alpha elimination. In the last class we were trying to show you the examples of alpha migratory insertion, and in a lot of example we have discussed regarding that. We will discuss one more time the transition metal carbene, which we have started discussing in the last one, and then we will move to the alpha elimination. So, today's topic mainly will be on alpha migratory insertion and then alpha elimination. Okay. So, transition metal carbene, as we were trying to discuss, transition metal carbene, these are the complexes of this nature where R group is there, carbene as you know. This is the metal carbene species and there is a R group. This R group can be hydrogen or any other alkyl group. So, this is alpha migratory insertion we are looking at. The reverse will be the alpha elimination process. Now, if this R group is H or if R group is methyl, depending on that we can follow the reaction and we will be able to tell the delta G double dagger of the reaction, and we can experimentally measure that. If we do that, for example, in case of this titanium complex where you have R and C5CH5 and no, this in this case particularly it would be C5Me5 and C5CH5, this complex was taken. This tetracoordinate tantalum complex was taken, and what was found is this tantalum complex having alpha migratory insertion happening, and in particular we have taken two different R groups. Okay. This R group can be two different one, and we can have the product formation. Okay. When R equals hydrogen and R equals methyl, what was experimentally found that this delta G double dagger value for in kcal per mole, this is 16 and this is 30. So, as you can see with hydrogen R equals H, we have the lower activation barrier, but for the methyl it is having a higher activation barrier. How much difference is there? That is 14 kcal difference between these two. How much difference is there again? 14 kcal. Now, H versus methyl, which one is faster? H is faster, right? This one is the faster. Now, 14 kilocalorie per mole, this energy is equivalent to 10 to the power 10 times rate difference. So, that is quite a lot of rate difference, right? 14 kcal per mole rate difference is there between the R equals H and R equals methyl, and this is experimentally given data. That means total this 14 kcal per mole difference would add up to something like 10 to the power 10 time rate difference. That is very faster, very fast for R equals H, and comparatively R equals methyl will be very slow. Now, of course, I think you may be aware of how to somewhat calculate a little bit what will be the energy difference and thereby how much will be the rate difference approximately. So, I am trying to give you some approximate sense. So, almost the rule of thumb, it's a very generalized thing, but not accurate, that very accurate. We are trying to give you a ballpark figure. So, approximately 4 kcal per mole equals 10 to the power 3 times rate difference. If there is a difference of 4 kcal per mole, the delta G double dagger value, then there is you should expect 10 to the power 3. In this case 14 kcal per mole value difference is there, and thereby you are looking for something like this is again a very rough calculation. So, that would be again 10 to the power 10 approximately 10 to the 10 times rate difference will be there. So, again this is not really the exact way, but this is how the experimental chemist kind of quickly calculate how much rate difference is there. The rule of thumb again is 4 kcal per mole, delta G double dagger difference. That means that 10 to the power 3 times rate difference is there, and if it is something like 14 kcal per mole, that will be calculated to be 10 to the 10 times rate difference, and it's a lot of difference of the rate. Now, let us try to look at what are other possible scenarios for the alpha migratory insertion. There are other cases where you can expect alpha migratory insertion, and then those cases include, let us say, other alpha migratory insertions. Then you can have this sort of complex. Again, you can get MCR. You can have this sort of complex as well. That would lead to MNR prime R. Okay. So, these are other alpha migratory insertion that is possible out there. You can look at the organometallic complexes, different complexes, and try to judge yourself where the alpha migratory insertion will be possible. But mainly I think in common literature you will see mainly the carbon monoxide is one of the major target for these alpha migratory insertion, and then perhaps the carbene examples comes to mind, and the others are less likely. Okay. But of course, you should keep your eyes open for such transformation. The next we will move on quickly to the alpha elimination, right. We will discuss that the reverse process of alpha migratory insertion, that is alpha elimination. As you have already know, this is mainly the CO elimination step we are going to discuss. This is what is going to be alpha elimination, then MrCO. These are the complex formation, and if this is n electron complex, you are going to get n plus 2 electron complex, right. So, these things you should be able to do very quickly, and you should not have any problem in discussing that. So, once again what is the alpha elimination? It is the reverse of alpha migratory insertion, and once again the common fact or common compounds where we can see such alpha elimination is the carbonyl species or the acyl species, for example MCOR, from where the R will be now transferring to the metal center. The n electron count of the metal center or metal complex will be giving you n plus 2 electron count. Now, these are the facts which is true both for alpha migratory insertion and alpha elimination. In both these cases, we know that the 2 electron difference will be coming up. Let us try to discuss one of the example where I am sure you have seen it before. This is the decarbonylation reaction. Okay. Decarbonylation reaction means, let us say you have a metal acyl species, from there, or so to speak, you have a aldehyde as a complex RCHO. From there, by involvement of a organometallic intermediate, you are trying to form RH, aldehyde to, let us say, alkane formation. That is the one very simple example that demonstrate alpha elimination reaction quite beautifully. Let us look at one of those examples. So, the decarbonylation of aldehyde, decarbonylation of an aldehyde. What we are having? RCHO to RH, right. So, the CO is going out. Now, simply the most common one could be benzaldehyde to benzene, right. As you may have known that this is a reaction which has been done by using the Wilkinson complex. What is Wilkinson complex? That is the rhodium complex RHL3Cl, where L equals your triphenyl phosphine. This Wilkinson complex reacts with aldehyde, let us say any common aldehyde RCHO. If you hit it, you will get RH plus rhodium L2Cl CO complex along with the ligand coming out. So, how these reactions are happening, this is what we would also like to know. Where is the alpha elimination, or how is the alpha elimination occurring? So, this is the Wilkinson catalyst. What happens? Wilkinson catalyst can react with the aldehyde. First step would be the dissociation of the ligand and you will have RHL2Cl. One of the ligand goes out, this is a triphenyl phosphine in this case, and you will have RCOH, then oxidative addition into it. So, we are going to see the oxidative addition over there, and that will give rise to the complex where rhodium hydride and COR is involved. From here you can see that this is the complex which is the oxidative addition complex. The metal is inserted basically into this carbon hydrogen bond to give this intermediate. From there, this is the perfect complex, as far you can see there is metal COR group involved. Then you can have alpha elimination. This is the step alpha elimination. The previous step was oxidative addition, and you can get Cl L2 rhodium COH and R, right. And then this R and H should be cis to each other, as you know that by reductive elimination you should get the RH product. So, what we have seen here is very simply the Wilkinson catalyst, rhodium catalyst tris triphenyl phosphine rhodium complex with chloride can undergo first a ligand dissociation. In this case, triphenyl phosphine ligand will be dissociated to give you rhodium triphenyl phosphine complex with chloride, which then can oxidatively undergo addition to the aldehyde to give you this metal hydride and metal acyl species. From there, as you know, that species is ready to undergo the alpha elimination reaction to give you the intermediate where R and H will be sitting together, and once they are cis to each other, they can reductively eliminate to give you the RH. So, let us look at the reaction one more time. This is the Wilkinson catalyst, ligand dissociation gives you RHL2Cl, and then it gets into the aldehyde to give you the oxidative addition complex. From there, elimination of this CO gives you this complex where R and H can now be cis to each other to give you the reductive elimination, and finally you get the RH. So, overall what you have seen in this reaction is your aldehyde effectively is converted into the alkane. So, benzaldehyde can be converted to benzene. Let us say you have aliphatic aldehyde that can technically give you the alkane with one less carbon. So, this is actually one of the really important reaction where you can see that something like biomass can be converted to corresponding alkane to give you the fuel grade alkane. So, these are very simple reaction, but can have very long term effect. Of course, in addition to rhodium, now we have seen that that palladium can do the job. Rhodium, iridium can also be okay, but palladium is also very effective for such aromatic aldehyde decarbonylation reactions. Okay. Now, you have seen one of these example. Let us move on to the alpha elimination of transition metal alkyl species, which is again analog of the one what we were discussing. So, alpha elimination of transition metal alkyls. Now, in these cases you can have one compound like this, where you have a isopropyl moiety in there, and then these are the transition metal alkyl complex. If it undergo alpha elimination, you are right that it will give you this complex, that means the carbene complex. Once again, if this is n electron, this should be n plus 2 electron. Now, this is the same if you look at the alpha elimination we have discussed with the CO and R group, MCOR, it is exactly of the similar type, that here again a alpha position elimination is going on, and the group is now sitting after elimination, it is now sitting with the metal complex. Of course, in this particular case we are going to get metal carbene complex. Let us take one of the particular example which demonstrate this alpha elimination of metal alkyl species. This again a very elegant example. This is by Professor Strock's group, Richard Strock at MIT. They have shown that this tantalum complex can give you this tantalum carbene intermediate, okay, along with L, H and I, L, rest of the things remain constant. In this particular case, K equilibrium is nearly 1. So, this is again one of the very beautiful example that demonstrate that alpha position of this one. This is the alpha position, this H is now migrated over there. This is alpha elimination of transition metal complex. Now, next we will move on to beta migratory insertion, where we will see that so far we have discussed the alpha positions are getting converted or getting eliminated, or some transformation is happening at the alpha position. That means the carbon center which is immediately attached with the metal are undergoing some changes, but it could be also possible that not the alpha position, but the beta position is the second carbon from the metal center is undergoing some transformation. Indeed, such beta migratory insertion or elimination are very much happening in the organometallic complexes, and those are the one which are perhaps more important of this genre. Let us look at the beta migratory insertion. Now, most common one for beta migratory insertion is the one where, let us say, you have metal with a olefin coordination and hydrogen coordination, and they will undergo a concerted syn addition. That means you have metal H, sorry, from there you can have this concerted reaction where it is a 4-center reaction going on. You can have a transition state like that. This will be a concerted syn addition, and from there on overall you will be able to have a complex where this alkyl group is over there. So, what we have seen here is metal hydride with a olefin coordination undergoing concerted syn addition in a 4-center mechanism, and from there on we have seen metal alkyl species is getting generated. Now, this is a very common reaction that is observed in a number of industrially relevant process where beta migratory insertion is happening. The most famous one could be the hydrogenation, hydroformylation and Ziegler-Natta polymerization reactions. Now, let us try to look at one of the most critical or most common reaction of these, and actually we will be discussing quite a lot on these beta migratory insertion or the elimination reaction. Slowly let us look at one example at a time. So, the first key step in this, the key step in a number of reaction these beta migratory insertion are involved. So, the one that comes to mind is the hydrogenation. Any hydrogenation reaction you have studied, there will be beta migratory insertion. Hydroformylation, of course, Ziegler-Natta polymerization is another one. Now, the first discrete example was with a platinum complex in this case, where we can see that first discrete example of this type are the one where once again the metal hydride and the olefin is coordinated to give you metal this alkyl intermediate. This was demonstrated in 1962, where we have seen that the metal olefin and hydride will be the complex was synthesized, and then upon beta migratory insertion we can have the metal alkyl species. Let us take that particular example in mind, and that metal hydride ligand and the chloride ligand in this particular case is triethyl phosphine. Under 40 atmosphere pressure, when the ethylene gas was passed or reacted, and we can see the product formation. In this case particularly, let us say with platinum, it gives HL chloro and ligand. So, this is one of the first example that we have seen in 1962, way back in 1962, this was discovered, where metal complex was reacted under pressure with olefin to get the metal alkyl species. That was the genesis of a completely new and interesting area, which has been commercialized in many form, in many different important reaction, that is the beta migratory insertion step. So, we will discuss further on this, and how the, of course, the insertion step, beta migratory insertion, also we would like to learn how the migratory aptitude varies from one R group to the another one, and also a number of synthetically and industrially important reaction we would be discussing in the next class. Till then, keep reading, and we will be discussing more on this topic. Thank you. Bye bye.